Thank you. It really is an honor to even be considered for this award. I'm grateful for this opportunity that I have to give an address, and I'm going to talk about physics, of course. Physics for all. All right, so I want to start out with what is the state of science literacy in America? And Neil deGrasse Tyson, he said this just last year: Americans overall are bad at science, scared of math, poor at physics and engineering, resistant to evolution. The science illiteracy is a threat to the nation. The consequence of that is that you breed a generation of people who do not know what science is, nor how and why it works. You have mortgaged the future financial security of your nation. Innovations in science and technology are the basis of tomorrow's economy. Here's some data that backs up what he's saying. We look at ACT data, college and career readiness, and you notice science is where students are doing the worst, with a close second being mathematics. So math and science are the two areas that students are doing the worst at the high school level as far as their preparation for college. So here's a quote I thought was interesting. A student's ability to enter and complete a STEM post-secondary degree or credential is often jeopardized because the pupil did not take sufficiently challenging courses in high school or spend enough time practicing STEM skills in hands-on activities. We have a problem in America. Students are not taking rigorous enough science courses and math courses in high school. So we need to change our paradigm. We need to understand that we can do hard things. And taking physics in high school is what I consider an example of doing hard things. So as I share experiences about high school physics, I'd like you to think about how you can extrapolate this to your life. You're out of high school, so how does this apply to you? Okay? Think about the hard things you can do. Think about the challenging courses you can take here in college. Or if you're a professor, what can you do to help improve the understanding, the scientific literacy of those students that you teach? So look for the hard things that you can choose to do. This is what high school physics in America looks like. So since 1997, that's when Lone Peak High School opened, nationally high school enrollments have increased by about 10%. As you can see this data, the most recent data that we have from 2013 shows that just slightly over a third of students take a high school physics course. So why don't students take physics in high school? Perhaps some of you can relate to this. It's too hard. There's way too much math. I have to maintain my high GPA. Can't get a good grade. It's only for the smart kids. It's not required for graduation. I'm not going to study it in college, so why should I take it in high school? I plan to study medicine, so I won't need it. I always laugh at that one, but that's a legitimate response that students give as to why they never took it. And then they get to college and find out that they wish they had. Counselors steer kids away from physics. This was one that was particularly troubling to me. And then also, most parents never took physics, so they don't encourage their kids to take it. So many times I get at parent-teacher conferences, I have a chance to visit with the parents, and their first thing is, I never took physics, so I don't know where my kid is getting it, but they're enjoying it, they're doing it. It's really an interesting phenomenon. But yeah, a lot of parents never took physics in high school, and so they don't encourage their kids to do the same. The American Physical Society released a brochure that has 7 myths about high school physics. So I want to look at the myths and look at the facts. So the first myth is that physics will lower students' GPAs and hurt their chances of getting into college. Fact, colleges want to see that students have taken challenging curriculum, and a B in physics is often better than an A in a less challenging course. Myth number 2, students won't miss out on future opportunities or experiences if they don't take physics. Okay, that's, why should I take it? I'm not going to miss anything. Fact, physics answers questions about the world that no other field can. In addition, not taking physics closes the door on a huge number of potential careers. Myth number 3, only the most mathematically advanced students can handle physics. Fact, physics can be taught at a variety of levels for students with different mathematical backgrounds. And I'll talk about how I deal with that in just a minute. Myth number 4, physics is for boys. Okay. Yeah. Fact, over 600,000 girls take high school physics each year, nearly half of the nation's enrollment. In fact, this year in my physics classes, I have one section of physics that I'm teaching that has 25 girls and 7 boys in the class. So, myth number 5, students don't need to take physics in high school because they could just take it in college. Fact, research shows that students who have taken high school physics do better in college physics, which are required for a large number of degree paths. So students who don't take it in high school because, I could just take it in college, they come to college less prepared to succeed in those college-level physics courses. Myth number 6, physics knowledge has little relevance to the world we live in or to most jobs. Fact, physics is fundamental to every other science and to most major technological innovations of the past century. Moreover, physics teaches critical thinking and problem-solving skills that are useful no matter what a student goes into. And myth number 7, the only careers you can have with a physics degree are to be a professor or to teach high school. And well, that's what I do with my physics degree. But, fact, physics opens the doors to a wide variety of excellent careers. Physics majors have high employment rates and are among the best paid of all college graduates. So with those myths, okay, if these myths were true, why would anybody take physics? Okay? Obviously, those myths are not true. However, sometimes hard things are forced upon us in life, but sometimes we get to choose to do hard things. At this last general conference, Sister, I just lost her name, Michelle D., I can't remember her last name, Corden, thank you, talked about how when she was a young girl, there was a pathway that she would take home, and there was a steeper, harder pathway that she would choose to take. And she chose to take that pathway because it was hard, because she thought that doing that hard thing would prepare her for the hard things that would come later in life. We will all be faced with hard things in life. Sometimes they come at us without our choice. Sometimes we can choose. When we choose to do hard things, we prepare ourselves for the hard things in life that will come to us later. And we get that confidence that we can do hard things, that we know that we can do hard things. Taking physics in high school or college is a choice. That can be a hard thing. So currently, to graduate high school in Utah, as far as science credits go, this is what it takes. 2 credits from the 5 science foundation areas. And this was actually news to me because I always thought there were 4, but there are 5. And earth science, biological science, chemistry, AP computer science, that was new to me. That receives high school science credit, or physics. So those are the 5 areas, so you need 2 of those credits, and then 1 credit either from the foundation areas or from an advanced or applied science list, things like astronomy or botany, those types of things. And so physics essentially is an elective course. You don't have to have physics to graduate. You don't have to have chemistry to graduate. You don't even have to have biology to graduate, okay? But that's what it takes to graduate. Now, just graduating and applying to and being accepted to a prestigious university, that's a different story. They'll have their own requirements. But just to graduate high school, physics is clearly an elective course. It's not required. So to give you a little bit of history about Lone Peak, where I teach, a suburban public high school has grades 10 through 12. It's located in Highland, between Provo and Salt Lake. It's just north of the Mount Timpanogos Temple, if you're familiar with the area. There are 9 traditional public high schools in Alpine School District, and the 10th one is actually opening up next year. Demographics of Lone Peak, not a lot of diversity. So I can't really speak to diversity because our population is about 95% Caucasian and relatively high socioeconomic status. You know, we have, it's not everyone that's that, but as a large percentage, our school is mostly Caucasian and relatively high socioeconomic status. So that's the lens through which I'm sharing my experience. So be aware of that. So when we opened in 1997, we had 1,400 students. And just this past year, we had over 2,500 students was our student population. And as was mentioned, the percentage of graduates who took at least one physics course, the first year, class of 98, 15%. And the class of 2018, that number is 80%. Lone Peak High School currently has 4 full-time physics teachers. It's not enough for one person to handle. When you get physics to where students want to take physics, you've got to get more physics teachers. So what made the difference? How did we go from 15% to 80%? Think back on those reasons why people chose not to take physics. Think back on those 7 myths. That's why 15%, that's why people were not taking physics. And the 80% is because we debunked the myths. We showed them it can be done. We encouraged them to do hard things. The key stakeholders in an effort to increase enrollment are the students themselves, counselors, that's a big one, parents, also a big one, siblings, other science teachers, and administration. So these are kind of the key stakeholders that we work on to improve or increase the enrollment in the physics courses. It takes time. It didn't happen the first year. It didn't happen the first 5 years. It didn't happen the first 10 years. It took a long time to progress from that 15% to the 80%. We'd love to see it get higher, but it's kind of plateaued around 80% for the last few years. Basically, one of the most important things is get the support of counselors. The students will go into the counselors to decide what courses they want to take. And if the counselors say, oh, don't take physics, they're not going to take physics. So getting them on your side, inviting counselors to see what you're doing in class, and have success. When students start having success in physics, it creates word of mouth advertising. Students want to take physics because their friend took physics and had a great time. The same holds true for gaining parental and administrative support. The effort needs to be persistent and continuous. Every few years, an administrator will come and go, and I have to resell them on the idea that physics is for everyone, that it's not just for the smart kids, the quote-unquote smart kids. Every kid is a smart kid, so every kid should take physics. So as administrators come and go, we have to tell them, because they come from other schools where physics is taught to 30% of the kids. And then they come to Lone Peak and it's like, well, these students can't handle this. It's too hard for them. No, they can. They can. And so usually it takes an effort to re-educate as administrators come and go, as counselors come and go, to re-educate them about the fact that physics is a course that everyone can be successful. So what can we do to encourage enrollment in high school physics? I want you to use your imagination here for a minute. Imagine that you're a physics teacher, or maybe you're a parent of someone who's in high school. Maybe you have a sibling who's in high school. Maybe you're a STEM professor looking to improve college STEM enrollment. Okay? So just kind of put that hat on for a minute. What are some things we can do to encourage enrollment in high school physics? Well, let's think about these 3 questions. As a physics teacher, what do I teach? How will I know students have learned it? And what will I do for students who have not learned it? So those 3 questions to consider. What do I teach? How will I know they have learned it? And what do I do if they have not learned it? Not every student is successful on their first attempt. So what do I teach? Well, part of that is determined by the state. The state has a core curriculum for physics, and that basically outlines what we should teach in a physics class. The idea of a core curriculum is that it's the bare minimum. It's not a list of you must teach this and only this, and it's not a list that's so long and exhaustive that you can't possibly cover it. It is truly a core curriculum. It's the basics of what students taking physics should have, so that students who took physics at Lone Peak or at Provo High or at Spanish Fork or anywhere in the state, you can trust that they have that same basis of physics knowledge. So we need to know the state standards. We also need to identify the essential standards, because even with the state core, some standards you may want to emphasize more, even though you'll cover them all. You may want to emphasize more on some of them. So you may be unable to teach every standard with equal emphasis. The American Association of Physics Teachers produced this statement on high school physics courses in 2015. They recommended the following characteristics for an effective high school physics course: clearly articulated learning objectives based on a small number of core ideas and science practices, learning assessments closely tied to those learning objectives, pedagogical structure based on physics education research, and then this is the part that I wanted to emphasize, limits the number of topics so students have adequate time to develop deep conceptual understanding as well as qualitative and quantitative problem-solving skills. Significant inquiry-based laboratory work, including experimental design, and accessible to students who are completing a math course at the Algebra 2 level. Presumably, Algebra 1 level is 9th grade, Algebra 2 level is 10th grade. So the way I read the statement, let's have sophomores take physics. That's what we do at Lone Peak. What do I teach? What are the most essential learning targets for each unit? So what do I want students to know? What do I want students to do? So we've developed these outlines of what the learning targets are that we want students to be able to know, what we want students to be able to do. We also provide for students an opportunity to self-assess so that they can look and determine where they are in terms of understanding each of those standards that we've set up. So for example, we give them a handout like this, and they will look at the standard. Can I use a kinematics graph to determine displacement, velocity, and acceleration? I might be at a level 1, a 2, a 3, or a 4. So they can keep track of where they are so that they know what their understanding is on the different standards, and they know what questions they need to ask if they need help. Teach them math with the physics. Assume they've been exposed to the math before, but that they don't remember how to do it. I treat that as a valid assumption. I assume you know how to rearrange F equals MA to solve for A, but let's just show you how to do it anyway. I assume you've seen the quadratic formula before, but let's review how to do that. So I teach the math with the physics, assuming they've seen it before, but they don't remember how to do it. So for example, in Unit 1, we teach the following skills: graphing from data and from an equation. So can I get a bunch of data and create a graph? Can I take an equation and show what the graph looks like? Finding slope and intercept of a linear graph. Finding the equation of a linear graph. How to rearrange an equation solve for a particular variable. These are some basic Algebra 1 level math skills that I assume they've been exposed to, but I don't assume they remember how to do it. So basically, if they're going to need a certain math for a particular physics concept, teach the math they're going to need to be successful. Choose how to teach. How to teach is at least as important, if not more so, than what to teach. Get the kids up moving around. Get them collecting real data. Teach them skills to analyze. Okay? They collect, analyze, and interpret data early, and then use those skills throughout the course. Engage students in scientific discourse and the process of science. The class is not a class, it's a community of scientists. So you establish that early on. The students see themselves not as a student in physics, but as a budding physicist, a scientist in a community of scientists. Physics modeling, some of you may be familiar with this, some of you may not have heard of this, but physics modeling is a physics education research based method of teaching physics. And so we have adopted this. I was actually one of the early participants in the modeling workshop project at Arizona State University. But basically, in your traditional science classroom, the teacher lectures, gives you a bunch of information, and then you'll do a lab that verifies the information that they just told you. In a modeling classroom, you begin the unit with a lab, what we call a paradigm lab. Students are collecting data, they analyze the data, and then physics principles are extracted from the analysis of the data. That's what we call the model development. They then take those principles that they learned from the lab and apply them to new situations, what we call model deployment. And so, for example, throughout the year, I refer back to the dune buggy lab whenever I want to talk about constant velocity. Talk about the ball on a ramp lab when I'm talking about acceleration. Because they have that experience, that's where they first experienced that. They remember the principles that are connected with their experience in the lab. Make it fun. Physics is fun. You get to play with all the cool toys. That's what physics is all about, playing with toys. Make it fun, okay? Get them up, get them moving around, make it fun, but students should be doing science, not just having fun. So yeah, we get them up, we get them moving around, we get them doing fun things, but you know what? They're gonna collect some data. They're not just playing with a little battery-powered dune buggy, They're gonna measure position, they're gonna measure time, they're gonna collect some data, they're gonna analyze the data, they're gonna create a scientific report on the data that they've found. Have high expectations of students. Every student is a smart student. Every student can succeed. Hold students accountable. Lots of fun in the physics classroom. But again, hold them accountable. Students aren't just having fun, they're doing science while they're having fun. That's the egg blast. You know, some of you have experienced where you build something to drop an egg and keep it safe. We blast it at the brick wall with compressed air, high velocity. You can see all the debris. It was some good times there. So yeah, it's physics. It's all about having fun, but doing science and learning principles while you're having fun. So how will I know students have learned? In education speak, we talk about formative assessments and summative assessment. Basically, formative means while you're learning, and summative means after you have supposedly done the learning. So on the summative side, you got things like lab reports or unit exams or projects. On the formative side, that's where you find things like a quiz every day, which I don't count for a grade. It's mostly a self-check for the students. They come in, they take the quiz, it tells them how they're doing. They understand, yes, I understand that thing from last time, no, I don't. And so that's what the daily quiz is. Whiteboard discussions, in-class problem sets, practice problems that we do in class. They can work in groups. Daily homework, I consider formative. And so I'll talk about that in just a minute. Show me boards, little 1 by 1 foot whiteboards. Students have a chance to draw a picture or solve a problem, and then they just hold it up so that you can quickly at a glance see where everyone's level of understanding is. And then things like Plickers or Kahoot. Some of you may know what those are. They're just applications or online services that also allow you to quickly review with kids or to assess in an informal setting. Lab challenges are great. So in the modeling cycle, after we've started with a paradigm lab, we extracted some principles of physics from the lab, and then they have applied those principles to new areas. It's fun to do a lab challenge where they get to apply what they've learned. So for example, the egg blast is here. That was one of the lab challenges. We talked about that. But there's some others like shoot the dime or the cannon lab, paper towers, bridge building. There's a lot of lab challenges that you can have students get up actually applying those principles in a kind of a laboratory setting where there's a challenge. Often the challenge is we turn it into a little competition, okay? So it's not just can the egg survive, it's whose egg survives where their device had the smallest mass. And so they have extra design considerations to take into account when they do those things. And so it just extends their thinking, helps them to apply those principles that they've been learning. So here's the Cannon lab, and I want to just show a little video. Basically, the setup for the Cannon lab is that each team is responsible for hanging one of these hoops from the ceiling and at just the right height so that when we launch the cannon, the ball will go through the hoops. So here it is, you can see it in slow motion. There it is, it's going through. And success and much celebration ensues. They were thrilled. So it's an amazing thing when they're able to actually get that right. I did all the calculations right. I measured out. I just need it's this far from the cannon. It's going to be this high off the ground. I hang it from the ceiling. Kids have a great time with that. Another great opportunity for physics is amusement park physics, the outdoor physics laboratory. So Utah State, for example, and Idaho National Laboratory sponsor an annual physics day at Lagoon, where they do several physics competitions at the park while the kids are there having a good time. Things like the Physics Bowl, ride design, where students design a ride and talk about the physics that's involved in the ride. The demonstration design, colossal G-forces, where they get to ride Colossus and build a homemade accelerometer, strap it to their arm, and then measure the acceleration on the ride. There's a logo design, smartphone activity, physics workbooks. It's a great opportunity for kids to realize that it's all physics. It's all physics there. And they get a chance to actually apply some of the physics that they've learned in that setting of the amusement park. Make it possible. This is one of the keys. Okay? The students who fear it's going to ruin my GPA. And Lone Peak has a lot of kids who fear ruining their GPA. Make it possible. Provide opportunities for them to demonstrate their competency. Consider things like resubmitting homework, retaking tests. We want students to demonstrate learning and understanding. Perhaps a little flexibility in when they demonstrate this could go a long way. So one of the things I do for homework, I use an online homework system, and it's changed over the years how I've done this. But basically, what we're doing this year, there's a system we're using. It randomizes numbers for students. So student A and student B, so while it's the same problem, they have different numbers. You can't just say, oh, the answer is 12, you know. But it randomizes the numbers. Students are given instant feedback to know if they're correct or not. So they just click in, yeah, it's right, no, it's not right. If they missed it, they could redo the question with the same numbers for a diminished amount of points possible. Or they can attempt a similar question that will give you new numbers and also resets the points possible. So a student can try again with the same numbers to make sure that they understand how to do it. Then they can attempt a new one with different numbers to verify that they know it, and it only will record the highest score. So in this way, the homework is formative. It's not like you missed it, too bad for you. It's a chance, oh, I missed it, let me learn from this. Let me make sure that I know how to fix this so that I know how to do this, okay? So only the highest score is ever kept. I do have a hard deadline on the homework, which is the day of the unit test. So they could redo the homework as much as they want right up until then, okay? And then my test policy, I let students retake a test one time. Recently at Lone Peak, we have taken to, instead of just doing a full-blown retake test, we've divided our test into what we call unit standards, those essential standards for the unit. And we allow students the opportunity to retake those standards that they did poorest on. They still only get one retake, but they can if we have 5 standards on the unit, they did poorly on 2 of them, they don't have to retake the whole test, they can just retake those 2 standards. And we record the test scores in their grading system as by standard rather than by unit. So students instantly know which standards they need to study and do better on. Also, we do set up a student who's absent for the original test only gets to take the retake. There are some students who were habitually absent on test days, and pure coincidence, but we simply have established that policy that if you miss the test, then that's fine. The retake is your test. You lose the opportunity to retake it after that. And so our attendance on test day has not been a problem. But or you get the student, oh, I missed the review day. Should I still take the test? Well, yeah, you should still take the test. If you do poorly, you do have a shot to retake it, but that's their option. All right, so in class, we often value collaborative work. We like working in teams, we work in pairs, we work in groups, we have lab teams, we do all kinds of things in groups. But then on exams, it's always individual. And so that sends a powerful message to students that, we value collaboration, except we want to see how you do individually. And so one of the things that recently I've learned about is a 2-stage exam. And I tried this the last couple years, and I found it to be pretty successful. So a 2-stage exam, and some of you may already be familiar with this, but a 2-stage exam, stage 1, you give the test in the original form. It's basically what we've done all along. Students work individually. Stage 1 counts for 85-90% of the grade. But then we do a stage 2, where students are working in small groups. There are a variety of ways to do stage 2. Basically, they're working in groups on the test. Okay? So they're testing in groups. Now, there's still the individual accountability, because most of the grade is individual, but this gives them a sense of confidence, because they're now able to discuss with people while they're working on the stage 2 part of the test. They're able to discuss what they're doing. I set it up so that stage 2 can help but not hurt their grade. So if they do worse on stage 2, which hardly ever happens, it won't affect their grade negatively. It can only help. So some options for stage 2 tests, you could select groups different ways. Teacher can assign, students can self-select, or the students can pick a partner, and then the teacher can pair up two partners. Lots of ways to assign the groups. Ways to do the test. They can retake the same exam. Just give them a new answer sheet. They can pick one free response and rework that. Okay? You're going to work this free response, you're going to work that one in a group now. You can do a shorter version of the test. You can do conceptual questions, ranking tasks, lots of different options. One of the things I did for my AP physics class is I would do stage 1 as a multiple choice and stage 2 as a free response, sometimes. And so it just gives you different options, different ways of allowing students to demonstrate their understanding. So there is a movement nationally to have students take physics first, which I agree philosophically with that movement. At Lone Peak, we do grades 10 through 12, so we try to get all of our sophomores to take physics. So I call it the physics second movement. That's what we're doing, physics second. So we encourage sophomores to take physics, which usually makes physics their second course, because they took a science course in 9th grade. This kind of stemmed out of when Lone Peak first opened. I was the only physics teacher, and one of our chemistry teachers wanted kids to have been in Algebra 2, already had Algebra 2, and I was like, physics, they just need Algebra 1. So we just kind of said, yeah, let's just set it up so they take physics first and then chemistry second. And there have been a lot of benefits from that. Our chemistry team, for example, right now, was recognized last year with Alpine School District as the Professional Learning Community Accent on Excellence Award, because for many years, our students actually doubled the proficiency on the state end of level exams in chemistry at Lone Peak. We were up in the 80% when the state average was in the 40%. And a lot of that could be attributed, well, we have excellent chemistry teachers, that's part of it. But we like to think, those of us physics teachers like to think that we're sending our kids to them a little better prepared. And so those kids that are taking that chemistry as juniors instead of sophomores, we've kind of worked out some of the sophomore stuff. And so the kids have figured out a few things, and so they're better prepared when they take chemistry in 11th grade. So part of it is to build a variety of resources for students to succeed, be available for help. We've created some ebooks, websites, video resources. My YouTube channel is Mr. E Science Theater, if you ever want to look it up. My claim to fame is my how to linearize graphs in physics. I've got 37,000 visits there, so that's my viral video. It's, just watch it. It's really exciting. Video resources, whether you made them yourself or you found them out there, there's a million resources out there for kids to be successful. Be organized, just provide resources for students to be successful. It's all about getting them to be successful. Put those supports in for struggling students. That's one of my favorite quotes. Parents, I've had 5 of her kids, and she said this: "It's always clear which teachers are student favorites when it's time to register for classes. You know something great is happening when physics is one of the more popular classes at a school. You know something great is happening when physics is one of the more popular classes at a school." There's only so much that you could do on your own, and so collaboration is the key to success. So Alpine School District does partner with Brigham Young University. One of the great opportunities that I have had is to be a mentor teacher to, and I actually have lost count as how many student teachers that I have mentored. Many of them directly, so over 16 that I've directly mentored, and many more that I have indirectly mentored because they have student taught at Lone Peak, perhaps with one of the other physics teachers at the time. And so I love having student teachers because they bring ideas, they bring enthusiasm. My philosophy is, here's all my stuff. This is how I do it. You do it however you want. Let them go. They are great. We've hired 3 of my former student teachers to teach at Lone Peak, and it was great. They're great. I wish they were still around, but they have moved on, and so I don't have them there anymore. But the 4 teachers at Lone Peak, we do meet weekly as a physics professional learning community. Every Monday we meet to collaborate, to talk about, what are we teaching, how are we going to teach it, how do we know if students have learned it. We look at data, we analyze how students are doing. And so those who can teach. You'll notice this graph from the Physics Teacher Education Coalition. There's some red over here in the physics and chemistry end. These are high school classes taught by a teacher with a degree in the subject. And so there is a critical shortage of physics and chemistry teachers. And so I'm just going to put in a little plug here for the BYU Physics Education Program. I'd like to say it was this good when I was here, but it is a lot better now than when I was at BYU. But BYU has produced more highly qualified physics teachers in the past 5 years than the number 2, 3, and 4 universities in the country combined. Okay? They've been nationally recognized multiple times for graduating qualified physics teachers. And I've had the opportunity to work with the BYU Physics Education Program as a mentor teacher. The 5+ Club is designed to recognize institutions that have graduate 5 or more physics teachers, qualified physics teachers, and BYU has more 5+ Club awards than any other university. The significant achievement, 5, you think, well, that's not very many, but when you look at nationally how many, the average number of graduates is 0 in physics teaching, and the ones that have the most, there's some that have 2 or 3, but the average is very low. And so they created this recognition for universities that graduate 5 or more per year. So those of you who are students, I want you to think about this for a minute. Consider teaching as a profession. There are job opportunities. There is a teacher shortage in physics and chemistry, and so the opportunities are there. Highly qualified candidates can expect multiple job offers. Holidays, vacation time, and job security. People say teachers are paid for their vacations. They're not. They're not. We're paid for the months that we're in school, and they just say, oh, let's take that and let's just divide that over 12. And so, it's not a paid vacation per se, but you get the same vacations as your kids. It's meaningful work. You're working with kids. You're teaching them. It's compatible with family. You get the same vacation, same days off as your kids. Job status and community respect, even though the media often doesn't portray it, those parents of those kids that you teach, you are held in high respect. It is a highly respectable position. The work is interesting. I love what I do, and I know I'm biased, but teaching is a great profession. One of the great things about it is, if you try something and it doesn't work, you can try something new next year, and then you can try something new next year. And so it's not just teaching, but it's that kind of that scientific spirit where I get to try something and see how it works. And if it works great, I can improve upon it. And if it doesn't work, I can do something different. You can do hard things. John F. Kennedy said the following: "We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because the goal will serve to organize and measure the best of our energies and skills, because that challenge is the one we are willing to accept, one we are unwilling to postpone, one we intend to win." Physics is a class in which every student can be successful. So what do we do from here? Don't shy away from rigorous courses. Embrace them. Embrace them. Hold high expectations of yourself. You can do hard things. Build in support systems that promote success. Take advantage of those systems that are available for you. And collaborate. Collaborate, share with others to improve teaching and learning. Thank you.